Alright, so this video is basically a slight continuation from previous video. In the previous video, I was talking about how to find nth Fibonacci number using matrix multiplication. And over there, we came across this identity fn plus 1, fn minus 1 minus f of n square is minus 1 to the power n. We were able to prove this using matrix multiplication in just one or two lines, right? Now in this video we are going to extend this to some other numbers, Lucas numbers and Bell numbers, and also discuss the generalized Fibonacci number. This is gonna be an interesting journey, I'm pretty sure, because I have enjoyed it and I will try to make sure that you will also enjoy this, right? Now I think you guys know this. Yeah, if you haven't like heard of this before, and if you want to get feel of this, you can just play with the numbers. We know that 0th Fibonacci number is 0, first Fibonacci number is 1, second Fibonacci number is 1 plus 0, 1, and then third Fibonacci, I don't know, anything, number is 2, fourth is 3, 2 plus 1, 3, fifth is 3 plus 2, 5, right? Now, if you take, let's say, f5, f3, and minus f4 square, you will get minus 1 to the power n, where n is this middle number, right? So let's see. 5 times 2 minus 3 square will basically be minus 1 to the power n is 4, right? So let's see this. This is just 10 minus 9, which is of course 1. So see, this works, and this is pretty fascinating. But yeah, if you go with the proof, then you may not feel so that I have given in the previous video. Now in this video, let's try to let's try for these numbers, right? In the previous video, it was pretty easy to grab this formula because we had matrix representation for Fibonacci number, right? F of n plus 1, f of n, f of n, f of n minus 1. We showed with induction that this is equals to 1, 1, 1, 0 to the power n. We proved this with the induction, and then we just took determinant on both sides, and that's why we said that f minus fn square. Determinant on this side is just minus 1. So we did it this way, right? But in this video, how do we find the determinant for Lucas numbers or generalized Fibonacci number, right? Okay, so we will see that. So yeah, but before that, I will just try to go into a journey of how do we represent recurrence with matrix multiplication, and slowly we will uncover how do we do this. Yeah. So yeah, our goal is basically to generalize to write nth Lucas number, which is defined by this expression as a matrix multiplication, and after that we will be able to prove this theorem that Ln plus 1 n minus 1th Lucas number minus nth Lucas number square is equals to 5 times minus 1 to the power n minus 1. Okay, now first of all, let's say let's see how to write the recurrence relation in terms of function. Okay, so let's say I have an plus 1, let's say this one, an plus 1 is equals to an plus an minus 1, right? Now if I want to capture this into matrix multiplication, what I can do is, let us say if I have an minus 1, this matrix representation, this of the sequences, right? And if I multiply this with 1, 1, 1, 0, let us see what I get. What I get is basically this 1, 1, and this will multiply and add with each other, right? 1 times an plus 1 times an minus 1, right? And this will just capture the first expression only, an. So this will now give me an plus an minus 1 will basically now be an plus 1 an, right? Now over here, what you can see is this matrix over here is just giving me next term for this vector. This next term for this vector and n plus 1th term for this vector, right? So that means if I again multiply by this vector with n plus 1 and n, I will get n plus 2 and n plus 1, which is just next term for this vector. So basically I can generalize the nth term for this vector by using this formula, and we know that over here an plus 1, an plus 1 or an, these are just defined by the recurrence relation, right? So these n plus, if let's say over here, if I write, now how you can see this is, if I write a0, let's say a1, a0, this if this is our first term, and this matrix multiplication basically encodes the way the reconciliation is set up. Over here I will get the second term for this reconciliation in first term, right? Now if I just go on, if power is 1, I will get second term. If power is, again, if I get another matrix, here will be 3 1, right? Power of 2, if then 2 and 1, basically we will get third term, right? So now if I basically write over here 1 1 1 0 times n in a1 a0, I will basically get the n times multiplied, so that will give me n plus 1th term and nth term, right? So you see that nth term can be the recurrence that gives us nth term, and going up to nth term basically can be captured through this matrix multiplication. Yeah, so you see how it's working. We are getting a vector with both the both the terms, and again we are getting both the terms, so that again you can use this to get another vector. So yeah, you also see that why both terms should be there, so that we can capture this phenomenon. Now let me show you somewhat general thing. This was simpler one, right? So let's say if I have an plus 1 is equals to, if there's 2, an plus an minus 1, how you can capture this? Okay, now over here, let's say I have an minus 1. Now what I want is, over here there should be an plus 1. Okay, I want the result to be an plus 1 and an, right? So that the same set of vector for n plus 1 term will be generated, right? Now I want an plus 1, an. So that the reason is, if I have this one, again I can use this with the same matrix to get another set of vectors, right? So yeah, so that's why I want this, because we need both the terms to generate another vector. So it's essential to write them in a vector form where both of them are there. Now to get this vector, we want first one to be multiplied by 2 and second by 1, right? So we get, right, 2 and 1. And over here we just want this first term, so just want the first term and others let it be 0. So we will just have an over here and an plus 1 over here. So this is how we can encode this recurrence relation. So now if there be, let's say, a1, yeah, if there be, let's say, a1 a0, right, and this matrix multiplying it, let's say, n minus 1th time, then basically you can this at one time this will give, if there's a1 multiplied 1 times, I will get a2, right? Multiplied 2 times, I will get a3, right? So basically you can see what the predict it by just adding this power and the substitute over here. So this one will give me an minus 1. You see that? Now this recurrence is captured by this, and we have already discussed how to raise matrix to a power. It's not that hard if you know eigenvalues and eigenvectors, right? So just using the matrix multiplication and how to raise matrix to power, you can solve recurrence relation. And so see, that's so powerful, right? Now let's go with other recurrence relation, how to capture them. Now let's say if you had something like if you had numbers in both the terms, let's say 3an plus 2an minus 1. In this case, what we would want to do is, there will be an and an minus 1, and we want to generate another set of vectors, another set of base vectors, right? So that you can again generate another vector. So an plus 1, an, you want this, right? How you can do is, you basically want to add 3 times this and 2 times this. So there will be 3 and 2, so that we will get this one, right? And for the second one, we just want the first one, so let it be 1 0. So yeah, this is how you generate the vector. Now if you want find the nth term, yeah, if you want to solve for nth term using the first 2 numbers of the sequence, is equal to a1 a0. You can multiply this by 3 1 2 0 multiplied by to the power n minus 1 to get a n and a n minus 1. See? Now let me show you how we do for if there are 3 terms. Now if there are 3 terms, let's say a n plus 1 is equals to, let's say 3a n plus 2a n minus 1 plus a n minus 2. In this case, how will you do? So now for every other vector, for every next vector with 3 coordinates, we need every like back vector with 3 coordinates, right? So we will basically want to capture all of them over here, a n minus 1, a n minus 2, so that we will again get 3 set of vector, and we know that all of these are necessary for the next one, right? So yeah, we need to capture all of them, a n plus 1, a n minus 1. All right, we want this vector again from this one, so that we will be able to move ahead and get to the last terms. Okay, now for this one, to get the first one, of course we need 3 times this, 2 times this, 1 times this, right? So 3 2 1, this will multiply this one, this row will multiply this column and give me that. Now for an, I just need the first term and not the other terms, right? So if I write 1 and then 0 0, that will just give me the first term. Again, now if I write 0 and then 1 and then 0, this will multiply 0 with first one, so I don't have that will just be discarded. 1 times this, so a n minus 1 will there, and again 0. So you see that I get this one. So this encodes the recurrence relation of the with 3 terms, right? Now if you want to encode with the and terms, let's say, I think this gives you an idea. Yeah, I will just do one for 4 terms, and then I think you will have the idea how to do. 4an plus 4an minus 1 plus 2an minus 2 plus an minus 3. I think now you have the idea. I will have an minus 1, an minus 2, an minus 2, an minus 3, right? And over here we want 4 4 2 1, and now 1 0 0 0, and then 0 1 0 0, and then 0 0 1 0. This will basically give me an plus 1, an minus 1, an minus 2. So this is how we can encode a recurrence relation using matrix multiplication, and this is really powerful tool. Okay, now if you know this, now we are good to go, right? If you know this, now we are good to go to proving these formulas, right? Now let us see how we can encode this Lucas numbers using matrix multiplication. Now Lucas numbers, for Lucas numbers, okay, I want you to understand these things. Now we know that for Lucas numbers, if I want, let's say ln minus 1, this will just be yeah, there will be 1 1 1 0 times ln minus 1 ln minus 2, right? Ln minus 2. I think you understand this, right? Because ln is just defined as ln minus 1 plus ln 1 minus 2, which is just given by this one, and second will just be ln minus 1. Yeah, so you see that, right? Now let's say if I have L0 L1 over here, right, and if I multiply with this same matrix n times, this will increase by n, so we will basically just have ln minus 1, right? Yeah. Okay, now what I further want to show you is if I have, let's say, L n minus 1 L n minus 2, we can get this number. I will write this as something different. I will write this as 1 1 1 0 to the power n minus 1. I'll show the reasoning later on, and here L1 L2. Since here already L1 and L2, now n minus 1 and 1 base will add up to give n anyways, n minus 1 and 2 base will add up to give n minus 1 anyways, right? So this, I think you can see why this world, because I have just like splitted one matrix and multiplied this with the L0 L1 to get this picture. Now there's the reason why I'm writing it like this. I want to show you something. And okay, now we can get this by multiplying this matrix to the power n minus 1 with L0 L1, right? So this basically what this does is, if L0 L1 is multiplied by n, this matrix by n minus 1, this 2 will add up to give Ln minus 1, and 1 in oh, I'm sorry. This was supposed to be written as, oh, I'm writing it the opposite way. Okay. Here supposed to be, in the numerator, it's supposed to be bigger number, right? So that the bigger number will be downside in the over here. Okay, it's supposed to, I'm sorry for this one, it's supposed to be L1 L0, because only then L1 will be here in the denominator of the next vector, right? So there's L2 L1. So I'm sorry for that. L2 L1. Now this will be n plus 1, I guess. Now if this 2 and n minus 1, this should be ln plus 1, and this should be just ln. Over here this should be n plus 1, and this should just be ln, right? Okay, fine. Now over here this is L0 L1. Yeah, now this is 0 and n minus 1 will be n minus 1, 1 and n minus 1 will be, oh, my bad. Again, this is L1 L0, right? Yeah, now this will be, what will this be? Ln and Ln minus 1. I'm sorry, man. And my n and n minus 1. Okay, now it's fine, I guess. Yeah, okay. Now it's finally good. Now this happens, yeah. Okay, now from here, using these two sets of matrices, this two sets of equations. Now how I will try to write them is, first of all, I will write this matrix Ln plus 1 Ln, and then write this matrix Ln minus 1. This will be given by the same matrix 1 1 1 0 to the power n minus 1, and then okay, now this was given by this thing, right? L2 L1, and this one was given by this vector, right? So L1 L0. I can write it like this. So basically what happens in matrix multiplication is, so this vector will multiply with this matrix to give the first pair of vectors. Again, second vector multiply with this matrix to give second pair of vectors, right? So this is basically the same thing. I'm just writing this to matrix multiplication in the single matrix multiplication. There's nothing different. This first vector multiplies with matrix to give first vector over here, and second multiplies with matrix to give second vector over here. Yeah, that's the same thing. Now, after we have got this, now we can finally use this relation to prove this formula, right? Now we know that L0 is 2, L1 is 1, right? And using this, I think we also need L2, and we know that L2 is just L0 plus L1, so L2 will just be 2 plus 1, 3. So L2 is 3, L1 is 1. Now I can write this as 1 1 1 0 to the power n minus 1 times this is 3, and this is 1 1, and then this is 2, right? Okay. So now we finally have this result, that Ln plus 1 Ln minus 1 is equals to 1 1 1 0 to the power n minus 1 times 3 1 1. Now we can take determinant in both sides and we will get the required formula. Yeah, this will basically be minus 1 to the power n minus 1, and determinant is commutative. I mean, what I mean is, if there's determinant of AB, I can break this into determinant of A, determinant of B, right? So yeah, we will take determinant in both sides and use this property, and then again, determinant of A to the power n is just determinant of A to the power n. So we will use these things to get to the following conclusion: minus 1 to the power n minus 1, and then this is 6 minus 1, 5. And that's how we prove this theorem for Lucas numbers, right? Okay, now let's try to go to Fibonacci numbers. Now let's try to do it a bit fast because I think you are adapted to the things now. So for Fibonacci numbers, if I want to get, now if this is the formula, we know that, let's say if I want to get f of n plus 1, f of n, f of n, f of n, f of n minus 1 with, by let's say a0, a1, and then I'm sorry, there should be a bigger number over here, a1, a0, a2, a1. With this, what I will want over here is, since 1 goes to n, it will have n minus 1 power, and then this set of vectors need to be multiplied by k and 1, right? So k a1 plus 1 a0, yeah, because that's the rule over here, yeah. Over here that will just be 1 0, right, because the first one needs to be conserved. Okay, yeah, so this is the rule for kth Fibonacci number. And now we know that the first few numbers, this will be by n minus 1, a0 is just 0, this is 1 1, and k times 1 plus 0, that will just be k, so this will just be k. This will give us the kth Fibonacci numbers, I mean nth Fibonacci numbers, nth generalized Fibonacci numbers, I'm sorry. Now if I take determinant in both sides, that will just give me fn plus 1, fn minus 1 minus fn square. This will just be minus 1 to the power n minus 1 time this will just be minus 1. So that gives me minus 1 to the power n. So yeah, so we proved this for kth Fibonacci numbers. Now interesting application of this generalized Fibonacci numbers is in Bell numbers, right? Basically Bell numbers are defined for k is equals to 2. If let's Bell numbers denoted by p is denoted by when k is equals to 2. So this sequence gives us the Bell numbers, right? And for this one we also define p0 as 0 and p1 as 1. Now since for any number 2, 3, 4, 5, we know that for any k, this is always this Fibonacci theorem also holds true in this one, right? So let's just take this to satisfy ourselves. So we know that p2 is just 2, p3 is just 2 into 2 plus 1 5, p4 is just 5 into 2 plus 2 12, p5 is 12 into 2 plus 5 29. And now let's try 29 into 5 minus 12 square should be minus 1 to the power 4, right? Now this is 145 minus 144 is 1, so it's true, 1 is equals to 1. So this holds true because it has to hold true because we have proved it. So yeah, this is what I wanted to share. Hope you enjoyed it, though I just messed up at some place in the Lucas numbers. Maybe that didn't ruin the fun. Yeah, I hope you got some new ideas. I hope that this was nice to learn or maybe fun to learn. Maybe you enjoyed it. If yes, do share with your friends too. Yeah, because such content will be there in this channel. And yeah, look forward to seeing you in the upcoming videos too. Please keep watching, keep learning. Also, just comment, suggest your ideas. Yeah, thank you.